This review covers Math 4's Unit 1 test or some Math 4's Module 5 test. The first question asks that we find the domain of the rational function. Remember from earlier algebra classes that a rational function is simply a function with a polynomial numerator and denominator. And remember, a rational number is a number that can be made into a fraction. So a rational expression, again, is an expression that has a polynomial numerator and polynomial denominator. When we go back to just rational numbers, there's a value that we were not allowed to have in the denominator of the fraction in order for that fraction to be undefined. And if you recall, that value is 0. We were not allowed to have 0 in the denominator of a fraction. With a rational function, we have the same issue. We are not allowed to have 0 in the denominator of the fraction. So when we're trying to find the domain, which means all of the x values that work, that give us a defined y value, we're still not allowed to have 0 in the denominator. So if we look at the problem, any number for the value of x that would make my denominator be 0 would not be part of my domain. So let's look at the first problem. F of x equals 3x minus 2 over 3. I don't have a variable in the denominator on this one, only in the numerator. So no matter what the value is that I chose for x, I would still have a number value for f of x when I plugged that value in for x. So that means there's nothing that would make my denominator 0 and nothing that would make this domain undefined. So the domain of the first problem would be all real numbers. If I wrote that domain in set builder notation, it would be x. Whoops, my pen's not on. Hold on just a minute. Okay, I believe I solved that problem. My domain would be x such that x equals all real numbers. In braces, that's called set builder notation. For my purposes, I would accept all real numbers. So the domain of that function is all real numbers. When I move on to the next problem, f of x equals 5x minus 1 over x plus 9, you can see that I do have a variable in the denominator. And remember, the exception to my domain would be any values of x that make that denominator equal to 0. So in order to find that, I'm going to take x plus 9 and set it equal to 0. So that means I just solve for x, which means I subtract 9 from both sides. And that gives me x equals negative 9. So that's the value of x that is not acceptable for my domain. Okay, we have our last two problems here. Now we have the rational equation f of x equals x plus 3 divided by x squared minus 16. So again, remember what we're looking at is our denominator, and I have to figure out what values of x would make that denominator 0. So I'm going to take x squared minus 16 and set it equal to 0. So now, on this problem, I can factor x squared minus 16, so I'm going to factor that. Of course, that's a difference of squares, which factors to x plus 4 times x minus 4. And remember, the zero product property says any two things that are multiplied and equal 0 means one or the other of them must have equaled 0. So I'm going to take each one of these, set it equal to 0, and solve. Now I have x minus 4 equals 0. And here, of course, when I move over that 4, I get x equals negative 4. And here, when I move over the I said 0 there, I meant 4. When I move over the negative 4, I get x equals positive 4. So those are the two things that x cannot be. So x cannot equal plus or minus 4. You could also write that in set builder notation, x such that x cannot equal plus or minus 4. Or you could put them in order, negative 4, comma, positive 4. For my purposes, again, just x. Whoops, forgot my cannot equals there. We want that to be not cannot equals, not equals. Okay, you could, for my purposes, you could just write x cannot equal plus or minus 4. In interval notation, this would start at negative infinity. It would go all the way up to negative 4, not including that endpoint, of course. And then it would go from, and I can put a union sign in between there or not, it can go from negative 4 to positive 4, every number in between those, but not those two endpoints included. And then it could go from positive 4 to infinity. So here's your set builder notation, here's your interval notation, or you could just write x cannot equal plus or minus 4. So that means your domain is all real numbers except plus or minus 4. So that could also be written in set builder notation as x such that x is a real number and x does not equal negative 4 and x does not equal positive 4. Alternate way of writing that set builder notation. Okay, now my denominator is x cubed plus 7x squared minus 8x in this new rational function. So again, remember that negative 2 minus 2x in the numerator doesn't matter when we're trying to find our domain, only the denominator does. So I'm going to start out with x cubed plus 7x squared minus 8x. I'm going to set it equal to 0 because I want to find the values of x that would make this denominator equal to 0, so that those would be exceptions to my domain. So first here I'm going to factor out the GCF, which is x. That leaves me x squared plus 7x minus 8 equals 0. And now I have to factor this trinomial. I'm looking for the numbers that multiply to negative 8 and add to positive 7, which of course are 8 and negative 1. So this becomes x plus 8 times x minus 1. The x I already have out in front has to stay there, of course. That equals 0. And now remember, zero product property says when you're multiplying things together and they equal 0, one or all of them could equal 0. So I have to set each equal to 0. I have x equals 0. I have x plus 8 equals 0. And I have x minus 1 equals 0. X equals 0 is simple. There's nothing else to solve on that. X plus 8 equals 0. I would move the 8 over to the other side with subtraction. That would give me x equals negative 8. And x minus 1 equals 0. I would add the 1 to the other side, and I would have x equals 1. Now remember, those are not the values that I want. Those are the values that I don't want. So x cannot equal each of those numbers. So in set builder notation, I would have x such that x cannot equal, and I'll put them in order from least to greatest, negative 8, 0, and 1. That set builder notation could also have been listed as x such that x is a real number and x does not equal negative 8, 0, and 1. In interval notation, that would go from negative infinity to negative 8. Then from negative 8, that's an 8, not an infinity. Looks pretty sloppy there, I'm sorry. That's an 8 to 0, a 0 to 1, and 1 to infinity. So again, for my purposes, you could also just say x does not equal negative 8, 0, and 1. Those are your domain problems.